Hi, hello. This is part 6 of chapter 3. And in this part, we are going to start discussing about quantum mechanics, which gives the specific details about where the electrons are present around the nucleus. Okay, so we are going close to that part in about a section. So this part is called the uncertainty principle, which is very much popular in both chemistry and physics. So you would so you would expect to see this topic again in physics if you have taken major physics classes as well. So the Heisenberg uncertainty principle says that it is impossible to know simultaneously both the momentum and the position of a particle with certainty. If, for example, he proposed it by based on Louis de Broglie theory that electron travels around the nucleus in the form of wave. So if it does travels around in the form of wave and not staying at a fixed position, so he said that you cannot pinpoint where it is present if it is constantly traveling. So you could only know with an assumption. For example, you could calculate the wavelength of the particle, right? We did calculate it in one of the problems as 1.6 times 10 to the power of -5 meters. So if it is traveling around the nucleus with some wavelength as a wave, so you could only comment on position of the electron around the nucleus with some degree of assumption, but you cannot accurately tell where it is present. So this is what called Heisenberg uncertainty principle. So this principle can be expressed in any one of these equations. Delta x is the position uncertainty for the particle in meters, and delta p is the uncertainty in the momentum. And you could also use the more elaborated equations, which you would most likely have to use the second one, where delta p can be redefined as the mass times the change in velocity. So mass in kilograms and the uncertainty in velocity. Both will give the same results. So if you didn't come across already internet about this joke, this is what this joke is about. Presumably, I don't think it is true, but this is a joke made above because based on his theory. So presumably, if Heisenberg is traveling really fast over the speed limit, and if a car pulled over and asked that standard question, do you know how fast you were going? And if the driver is the Heisenberg, he would say truthfully, no, but I know where I am, because he knows that he couldn't, if he sits in one place, right? He sits in his driver's seat, and if he is traveling, he cannot accurately tell, according to his theory, that he cannot accurately comment on his position and also the speed he is traveling. I hope you had a laugh on it. So I have here another fantastic video that I really want you to see. I'm gonna keep quiet until we finish the good part of this lecture. Then I'll take you back to work on a couple of practice problems regarding this topic. It is sound. Sorry, I lost sound. Let me check on it.
Today, I'm doing an experiment that demonstrates Heisenberg's uncertainty principle. So here I have a green laser, and I'm firing it down towards the front of the room through a narrow slit. And that slit can be adjusted, so it can be made narrower or wider. And the laser spot is projected onto a screen behind it. So what do you think is going to happen to this spot on the screen as I narrow the slit? Have a look. You see exactly what you'd expect. The spot gets narrower and narrower. The sides are getting cut off by the slit. Makes complete sense. And if you stop there, you would never realize that Heisenberg's uncertainty principle is at work. But if you keep going, something strange happens. You make the slit even narrower. The spot starts to spread out.
Let's see that.
Isn't that incredible? You're making the slit narrower, and yet the spot on the wall is getting wider. The narrower you make it, the wider that spot on the wall becomes. To understand this, we have to look at Heisenberg's uncertainty principle. Heisenberg's uncertainty principle is normally written as delta x, delta p is greater than or equal to h on 4 pi. So what does this mean? Well, it's about the position and the momentum of a particle. So x is the position of the particle and p is its momentum. So delta x is the uncertainty in position, delta p is the uncertainty in the momentum. Now, if you multiply those two quantities together, they must always be greater than or equal to h on 4 pi. Now, h is Planck's constant, and that deserves a video all to itself, like this one by 60 symbols. But for our purposes, it's just a very small number. So in our everyday lives, we don't come up against this uncertainty relation because everything is much, much bigger than h. But as we narrowed the slit, we were decreasing delta x for those photons. So we were getting more and more precise about where the photons were passing through that slit. And at a certain point, you come to this limit, so that if you narrow this any further, you're going to break this uncertainty relationship. So what needs to happen is the uncertainty and momentum needs to go up. I should specify this is uncertainty and momentum in the x direction, in the horizontal direction. So if before photons were going perfectly straight, now they must veer off to the left or to the right to ensure that we don't break Heisenberg's uncertainty relation. And the more you decrease your uncertainty in position, the more narrow you make that slit, the more the uncertainty in momentum has to go up. And so if these photons are going to the left and the right, that's going to produce a much wider beam. It's really, really non-intuitive, but it's the way the world works.
Must be the sun playing tricks with my mind.
What about, here's really going to test you, right? Tell me about what's well, this is a video. And I also have to say a big thanks to the University of Sydney for letting me use their equipment, and especially to Tom and Ralph for helping me set this all up. Oh, and just one more thing. I should point out that this explanation of the experiment is slightly controversial. At least in that Henry from Metaphysics and I have been debating whether it's really that counterintuitive. I mean, if you see light as a wave, then all light is doing here is diffracting. That's the phenomenon where if a wave passes through a slit, it bends at the corners and radiates out in all directions, and that explains the spreading of the beam. But that goes to the very nature of light. Is it made of waves or particles? That's something that I would like to explore in the coming weeks, so stay tuned for that. But Henry has an excellent video about Heisenberg's uncertainty principle, which I think makes it more intuitive and less spooky. So if you want to check that out, click on the annotation. It's a really good video.
I think this video is also excellent demonstration of Heisenberg uncertainty principle. And they did add it at the very last that maybe it is just the kind of double slit experiment for the light where it is having the dark region and a bright region, dark region and a bright region. But even if it is not accurately correct for the Heisenberg uncertainty principle, but the example itself sounds really convincing, right? If you try to narrow the laser light into small area, so you're trying to pinpoint the position of it. So the position, because you are going to break the h over 4 pi Heisenberg uncertainty rule, the position is splitting into parts because momentum increases. As you're narrowing the lasers dot, momentum is increasing. So that's why, because you cannot correctly pinpoint, light is traveling, laser is traveling, so you cannot currently pinpoint the position of it because it's already traveling. So that's, I think, a cool explanation. And even if it is, kind of little bit untrue also, it's just, good demonstration of the concept that, it is impossible to correctly pinpoint both the position and momentum at the same time. You can identify the momentum, for example, you could calculate wavelength easily, you could do that, or you can identify the position of it if you do not worry about how far it is traveling. For example, like using Schrodinger equations that we are going to talk about later in the next part, or even in this part. So let's work on this problem. So the question says that an electron in a hydrogen atom is known to have velocity of 5 times 10 to the power of 6 meters per second. About 1% of that, they were saying. Using the uncertainty principle, calculate the minimum uncertainty in position of the electron. They were asking for the position, the delta x, Given that the diameter of the hydrogen atom is less than 1 angstrom, comment on the magnitude of this uncertainty compared to the size of the atom. Let's look into it. So they gave you the velocity and they want you to identify the position. So it is already traveling and you know the speed, but they want you to identify position and see if you could, accurately predict where it is present compared to size of the angstrom, which is compared to size of the hydrogen atom, which is 1 angstrom. Okay, so because they gave you the velocity delta v, so you are going to use this form of the equation delta x times m delta v, because we know it is the electron that is traveling. So you know the mass of the electron in kilograms, which I'm going to show you now. It is the mass of the electron in kilograms, and the Planck's constant must be used in the kilograms to facilitate the cancellation of the units whenever you have a Planck's constant and a mass in the same equation. All right, so let's set up the equation. Let's rearrange that equation delta x times m delta v greater than h over 4 pi into delta u is equal to h over 4 pi delta x is equal to h over 4 pi multiplied with m delta u, because you need to identify the delta x. And once you plug in the h in kilograms value and m value and the delta u value, you happen to find that the minimum uncertainty in position is 1 times 10 to the power of -9 meters. Okay, and in terms of angstroms, it is about 10 angstroms. What is the question gave us is it is the hydrogen atom electron, and hydrogen atom has the diameter of 1 angstrom. So because you know the velocity, and if you're trying, because you already know the velocity with accuracy, because they said 1% of 5 times 10 to the power of 6. So the velocity is only 5 times 10 to the power of 4, because only 1%. Because you already accurately know the velocity, to identify the position of it now is really, really challenging, because it happened to be showing that 10 times larger than the hydrogen atom size. In hydrogen atom base, we are saying that electron can be anywhere here, anywhere in this room. See how crazy it is. That's what Heisenberg uncertainty principle is. You can correctly identify the position of it, or the momentum of it, but if you already know one, you cannot identify the another one with correctness. You can make an assumption like this, but your value is nowhere clear to its actual position. Okay. It just talks about how to use the correct units, but if you would like to have a read, please do. So what are we going to discuss now is where it is going to lead us to the electronic configuration. Excuse me. Remember, the chapter of this title is Quantum Theory and Electronic Structure of Atom. All we are doing here until now is to how to know more about electronic structure of atom. Obviously, in that process, we learned about the byproducts of the electron emissions, the photon, which travels or radiates in the form of wave. Most important equation in chemistry after after the identification of subatomic particles is the Schrodinger equation. Schrodinger equation is like kind of that huge breakthrough that explained everything to us about the electronic structure of the atom. So it is because of the work of the Schrodinger that we are able to correctly talk about where the electrons located outside of the nucleus, and what are their energies, and is it a small area where the electrons are located, or is it a larger area? So far, what we know, or what you know according to what we discussed, is electrons are around the nucleus in some kind of fixed imaginary area where they were traveling in the form of waves. But we do not know how the electrons are adjusted. We know that you could put in fit in more electrons as it is farther from the nucleus, if the orbit gets bigger. But we have no clue how they were arranged inside. Are they just mix and match, or if they have any pattern? Everything is explained by Schrodinger equation. So let's talk about it. And one nice thing for you, I can say, is you don't have to deal with Schrodinger equation in general chemistry classes. I'm just going to show you how it looks like. Let me just show you how it looks like. And I come back here. That's the Schrodinger equation that you would have to use if you take a physical chemistry class, but you don't have to use it in this class. But by the time you get really good in math and you get comfortable with chemistry, so that equation makes sense. But right now it might look a little bit, scary. But I have a great suggestion for you. If you'd like to buy a nerdy science shirt, that's totally a shirt that I would buy and wear it if I find it in a store. Let me go back. So Erwin Schrodinger derived a complex mathematical equation to incorporate the proposals of Louis de Broglie that wave is traveling like both wave and a particle. And he assigned a sign psi to the wave behavior of the particle that is traveling around the nucleus, the electron, and he derived an equation for this wave function psi, the particle that is traveling around the nucleus, to identify the electron density of the electron around the nucleus. So he's kind of said, yes, the electron travels around the nucleus, but there is always a high probability of where the more electrons are present. So he kind of gave us a shape, imaginary shape. Well, we shouldn't say imaginary, but he kind of gave us the ability to imagine how it would look like around the atom. For example, here you can see, this thick blue color, lighted blue color. What it means is, here you could find probably electron more likely and much higher density, also because of the small area, so electron is traveling. And the probability of finding electron here is much less because it is little less density. So you can still find it because there are still waves and colors, but it is less electron density. So once you derive this equation, you could correctly pinpoint where the electron is, what is the probability of it, and what is the shape of it, because his equation facilitates all of it. So using that, you could identify where to find the electron around the nucleus. That again, we don't go into the equation details in this class. You don't have to. I'm just showing this as an extra information because you just know what I'm talking about when I say complex mathematical equation. So the Schrodinger equation specifies possible energy states and electrons can occupy in a hydrogen atom. Excuse me, remember in Bohr's model, like in part 4 of this chapter, we showed when it is absorb the heat, electrons goes from N1 to N2, N1 to N3, N4, N5, N6, higher energy level states. So those energy states can be explained pinpointly by Schrodinger equation. Schrodinger equation will help us, identify the energy states, and also within the energy states where you can most likely find the electron cloud. For example, for a set of electrons, according to Schrodinger equation, you could say that electron would look like in this shape. Yes, it travels in a wave, but it would be found in this kind of shape called a p orbital based on its behavior. And based on its electron density, we started giving them names. So let me just give a try again just to make sure I was able to give my point across to you. So Schrodinger developed an equation, a mathematical equation, to predict where you can most likely find electrons at each energy levels. So if it is just one electron, you can find where it is. If it is more than one, like 2, 8, 18, 32, bunch of electrons in different energy levels, using Schrodinger equation, you can predict where you will find the electrons at different energy levels, and within energy level, in what shape they were present, how they were coiled, how they were, let's say, combined, how many they were grouped. So all of these questions are answered by Schrodinger equation. So again, let me repeat, we do not use his lateral equation, but we are going to use the results of his equation in giving labels to the electron location outside of the nucleus that I usually call kind of like a GPS of the atom for the electrons. So if you have, like, say, a hydrogen atom, it is only one electron. If you think about carbon, it has 6 electrons. If you think about aluminum, 30 electrons. If you think about zinc, it has 30 electrons. So as the electrons increases, you need to know which electron is present at which location, right? So we have that coding system to communicate one to another, where the electrons are, how far it is from a nucleus, and how it is shaped around that nucleus in that particular energy state. All of that is going to be discussed from topic 3.7. That topic is called quantum numbers. That's all for this lecture. I'll see you again in part 7 of this chapter lecture.